converter, and question about practical and unit diode models. And it's basically the ideal model, the practical diode model, and the exact model. And then a question involving Zener diodes in DC circuits. And it can be a question about rectifiers and filters, that's the half wave and the two full wave configurations. Linear binder can appear in a question, and also the difference in amplifier. Now, questions that are not expected, so the question, no question regarding the voltage level shifted circuit. And that circuit can appear in different versions. It will not be a question involving a Schmitt trigger, and there will not be a question about what's called mass stable multivibrator. We may cover that later on in the course. And then will not be a question about design of AC to DC converters using diode rectifiers, filters, and Zener diodes. And this part here, this is referring to the design of Zener diode regular power supply regulator. This is what we covered on the last session, and we'll just go to some of the problems that were presented there. So questions like this, where you're basically designing a complete AC to DC power supply using Zener diodes and then also regular silicon diodes. So we went over the design of a power supply like this that uses a transformer, and the transformer converts the large AC input into a smaller AC across the secondary of the transformer, and then there are various parts in here that we have to calculate. The line over here, this is the peak from the AC wall, 226 volts. The output of the transformer is DC mass, the capacitor peak, you can calculate that. Now this part about capacitor peak, and so this circuits like this can appear on the midterm. So this circuit like this without the transformer and without the Zener diode. So there won't be any calculations. We definitely can have questions regarding calculating ripple in a circuit using this formula here. This is the four-way rectifier. So this formula definitely should be on your formula sheet. These are ripple for a four-way rectifier here is a period over 2 times the RC in the circuit, and there's a simple version which is the halfway rectifier. So what we do here on your there are a couple files on the module. One is here, midterm review, that file, and then there's a second. there's a second file, it says op-amp review test. So we're going to briefly go through the first file. This file is a review of the op-amp and the diodes. And then the second file, it says op-amp review test. This is only about the op-amp themselves. So the first one we'll look at, and you have a copy in the modules on Canvas. We'll look at this file here first. So the version of the op-amp here, the inverting op-amp version is shown here. We out with minus RF of RS times the source. Non-inverting op-amp, the gain is 1 plus the feedback resistor R2 or R1. And the gain is no smaller than 1. And then the buffer, the positive buffer, or V out, is equal to V sub S. And so the basic op-amps. Low-pass filters, and this is given an example here. A filter with a cutoff frequency of 500 hertz. And basically it's not really showing the desired frequency, just saying the cutoff is 500 hertz. So we need this formula definitely to calculate the RC of the filter. So this version is saying we're going to assume the resistors are, and as I said, there's no need to memorize schematics. Any schematics most likely going to be given. So this filter is designed and has a feedback resistor RF, a capacitor C1, and a series resistor on the source 3.2K. So the cutoff for this filter is 1 over 2 pi RC. And this filter has a gain of 1. How do we know the gain of this filter is 1? The feedback resistor and the source resistor are the same value. So it has a gain of 1. And a capacitor was selected, 0.1 microfarad, and a resistor calculated. This capacitor could be 0.01. It could be 1 microfarad, 10 microfarad. The idea is to keep the resistors above 1 k ohm. So when you're solving a low-pass filter problem, it may be a better first attempt to select the resistor above 1 k and then solve for the capacitor. So the objective here then is if the problem does not indicate that the filter must have gain, then you just set this resistor and this resistor equal to each other and then solve for the capacitor. Of course, you'll have to select a cutoff. This problem already gives a cutoff, and the cutoff is much less than the undesired frequency. We'll look at a different problem that's similar to this. So that's just a plot. There won't be any simulation questions such as P-Spice there. So here's a version of a filter. This one needs to remove a 50 kilohertz AC signal with amplitude 0.5 volts from a desired 1 kilohertz AC signal with amplitude 5 volts. So we notice the desired 1 kilohertz is 5 volts. The undesired 50 kilohertz is 0.5. So you need a low-pass filter that will pass to 1 kilohertz. So the cutoff is greater than 1 kilohertz, but is much less than 50 kilohertz. And given hundreds of different choices, this design says let's just make the cutoff 5 kilohertz. That's above the desired 1 kilohertz and is far below the undesired 50 kilohertz. And if you go through the math here, you might find that the actual frequency cutoff was 2 kilohertz, but we'll leave that to your calculator. So this version here says, since the cutoff is, it says frequency, and notice here it says 2 times 10 cubed, so I guess this was an error on the printing here. So we put in 2 kilohertz, arbitrarily choose a capacitor, 0.1 microfarad, solve for the feedback resistor, 1/2 RF, CISO solve for RF comes out 796 ohms. This is less than 1K, so if you solve for something and you get a resistor less than 1K, you want to go back to the capacitor and choose a smaller capacitor, and that will increase the resistor above 1,000. And of course, the gain is set equal to 1, so the feedback of RF is set equal to each other. The circuit does not indicate that we need gain in it.
Does that mean that the amplitude of the signals don't matter?
The problem like this where it did not give the battery voltages here. And that basically is the attempt here. A real problem will ask you to design the battery voltages also. So if this problem had something added to it, also select the battery voltages, then the largest amplitude is 5. So if your batteries are plus or minus 10 volts or plus or minus 12 volts, and your gain is 1, the filter will not clip in the output. So the idea is that if the question says select the battery voltage, it's a good idea to compare your number to the amplitudes of the input. The best case is just set the gain to 1. And then if your batteries are plus or minus 8 or 10 or 12, you just decide on that. And this question is just similar to your homework question, so involving the Z number and as an AC amplitude of 3.2 volts. The Z number, the last 4 digits, the noise is 30 kilohertz, and this suggestion says the cutoff is 1.5 to 2 times larger than the desired frequency, and test the rest of it is P-splash. So we've gone over that already. This circuit here, a question like this is asking, aside from the P-splash, is asking to identify the amplifiers in the configuration. So it's 3 op amps. And what's the first op amp here? What's the name of this op amp cycle?
So, non-inverting. It's a non-inverting amplifier.
Okay, non-inverting, and the second stage is a
Buffer.
buffer, voltage buffer, and the third is a
Low pass
filter. And it actually has a fourth stage in it. The question didn't say identify all 4 stages. The 4th stage is a voltage divider on the input. So something like this is asking just to identify the circuits. And you want to also note if all the op amps share the same battery voltages. These all 3 operate off plus or minus 10 volts. One of them, let's say, if it operates off plus or minus 18, you want to check the battery voltage in the circuit. With that, we'll go to more op amp circuits in a moment here. Diodes, this is the ideal diode. It turns on with 0 volts across it. It turns off with any negative volts across it. And the diode has an anode on this terminal and a cathode, and it conducts current from the anode to the cathode. Whenever the voltage across the diode is greater than 0, an ideal diode becomes a short circuit of a wire. And whenever the voltage across the diode is less than 0, the ideal diode becomes an open circuit. And that's what this is attempting to show here. This diode we assume is off, so it's open. And over here, when the diode switches on, it just becomes a wire. So in a circuit. The practical diode turns on at 0.7 volts across it, and basically an actual practical diode turns on around 0.5. But if you're working in a circuit with a practical diode, the problem will just say if the diode is on, it has 0.7 volts across it, and that's it. Positive from the anode to the cathode. Solving diode circuits, write down all circuit equations, simplify as much as possible. Circuit equations are usually KCL, Kirchhoff's current law. Your first assumption is the diodes are either on or off, and basically you have to decide how you're going to make up a truth table depending upon the number of diodes. If it's a single diode, it's on or off. If it's two diodes, you have multiple states. If it's three diodes, you have even more states. So we'll go over a simple, we'll go over find one here. Here's an example diode questions here. And the problem doesn't indicate it here. We'll assume this is a 0.7 volt. So we don't want to off. Yeah, it's a 0.7 volt diode here. So the question is saying, once you decide on the state of the diode, you want to justify it. So here it says try the diode is on first. And what is V out that this diode is on? Being a practical diode.
0.7.
Current must flow in this direction here. So this practical diode must have 0.7 volts across it. If it's on, then the voltage, the current then through this resistor is 10 volts minus 0.7 divided by 1 k ohm. And we notice there are three connections here. So we have three, it's a KCL problem that's being we're looking at here. So the current out of a 10 volt battery is 9.3 milliamp. The current in this 1K load, we can solve it's 0.7 across 1K. And the diode, in order to avoid using the exact equation to calculate the current in the diode, we just use Kirchhoff's current law. So the diode current is the difference between the current in 1K and the current in this 1K, and we subtract 9.3 minus 0.7, so it's positive 8.6 milliamp, and there are no contradictions that this diode is on. It's all positive current. If we had started this with the diode being off, then the voltage here would have been 10 volts if the diode is off, and you find a contradiction because with 10 volts across this diode, it's not possible that it's off. So usually try diodes on first. The lowest circuit is a 1 ohm resistor across the diode. From logistics, you'll try the diode is on, and there's kind of a logic about the circuit with a 1 ohm load on it. The resistor 1 ohm is probably going to short circuit the diode. But still, we try that it's on, so if the diode is on, it's supposed to be 0.7 volts, so 0.7 volts across 1 ohm is 0.7 amperes, and the current from the 10 volt battery then is 10 volts minus 0.7 over 1K, 9.3 milliamperes. So there's a contradiction here. We only have 9.3 milliamp available. The load is trying to take 700 milliamp. That's a contradiction. So we go back and the diode is off. If it's off, the current through the diode becomes an open circuit, and you get two resistors in series. And now it's just a matter of solving using Ohm's law to solve for the current through both of these diodes. And the 1K just has the 1 ohm added to it here. So it's about 10 milliamperes.
Why do you add that one, why is it 1.001?
It has a 1 ohm resistor for it. So the diode is open, all the current flows through here to ground.
Okay.
So 1K plus 1 ohm.
Oh,
That's where the .001
oh.
comes from.
Yeah,
And diodes, multiple, so the question says, use a practical model if the diode is on. And when diodes appear in series, if one is on, they all must be on. If one is off, then all of them have to be off. So again, it has 3 sections, so there's a KCL. So it's asking solve for the voltage at this point, and then to solve for it, we need to find the current here, the current in this resistor, and also the current in R1. And which law is this being set up here?
KCL.
This is the KCL loop here. So 10 volts minus this unknown voltage V over 1K, and then the diode resistor R2 is just the voltage over 1K. This is just leaving off the K, and then the voltage here is V minus 2 times the diode drop, because we have 2 diodes in series, and then we solve, the only unknown is the voltage at this point, so we solve for that. It's 3.8 volts, and now we solve for, now we can go back and solve each one of these equations. The first one, the current here, I, 10 minus 3.8 or 1K, 6.2 milliamp. The second equation, I is 3.8 over 1K, 3.8 milliamp, and the third, with this voltage here, V 3.8 minus 2 times 0.7, and we get 2.4 milliamp. All of these currents are positive, and 3.8 plus 2.4 both add up to about 6.2 milliamp. So with that, we can say there are no contradictions, and it's justified that all the diodes are on. Multiple diodes with in a circuit like this. First, the question is which diodes are on, which diodes are off. There are many states to this logic here. We can rule out one of the states, which is all the diodes can't be on at the same time. So we can rule that one out. They can all be off, but that's another state we will not rule. So we look at these diodes, and we want to know whether the diodes are ideal or practical. If they're practical, each one requires 0.7 volts across it when it's on. If they're ideal, they become a wire. So the question is, what is the voltage here, and what is the current in this 1K resistor? And logistically, since only one diode could be on at a time, you basically want to scan the voltages and then you want to make a quick guess, because if you get a contradiction, it means you're going to go in a circular until you finally realize that maybe the simplest state was probably the largest voltage is probably going to dominate the circuit. So that's kind of a hint there. So what's the largest voltage? 3. So if 3, the diode D1 is on, D2 and D3 must be off. So if D1 is on, we'll write this voltage must be 3 minus 0.7. 3 minus 0.7 or 2.3. And now we need to justify, you have to justify D2 and D3 being off. So D2, if this voltage is 2.3, then D2 has a larger voltage on the cathode than the anode. So D2 is on. D3, if this voltage is 2.3, it has a larger voltage on the cathode than the 1 volt on the anode. So this diode is on. So you must justify, once you justify which diode is on, we go back and now justify the other diodes being on. And if there were 8 diodes here, you can basically imagine trying to go through all the states. So as I said, perhaps with logic like this, the largest voltage will dominate the diode being on, and now you just have to do the math and prove the other diodes are on. Rectifiers, this is a half-wave rectifier, and what we want to cover with this is how to calculate the ripple, and then how do we calculate the capacitor and the resistor based upon how much peak-to-peak ripple the circuit will have on it. And the ripple formula for half-wave rectifier is here. The peak voltage, and that's the peak voltage across the capacitor here. So if this is a 10 volt amplitude source, what's the peak voltage across the capacitor? This is a practical diode. So this is a 10 volt amplitude source. This is a practical diode. So what's the peak voltage?
9.3?
The 10 minus 0.7. 9.3. So there's 9.3. The frequency is probably given. The period T is 1 over F. And now we decide if we want to pick a capacitor, we're probably going to pick something in the microfarads to start, and then solve for the resistor, which means there are hundreds of results for a circuit like this. And so here is the formula for the half-wave. Ripple can be given as a percentage of the input signal peak, or it could be given as a voltage itself, like 1.2 volts or something. If it's given as a percentage, it's saying just do the math and calculate the peak ripple. Or if the ripple is given as peak, then you'll have the number. So usually the ripple is given, and you just have to calculate the peak voltage, the period, and then solve for the RC components. And this is an example here. This filter, the question says you want ripple of less than 1.2 volts, and how large should R and C be? Use a practical diode. The amplitude of the source is 18 volts. We have one diode, so the peak on the capacitor is 18 minus 0.7 is 17.3. And then we put that in our ripple formulas, factor out RC, and come up with 0.0952 for the time constant. And then we set RC equal to that. This version picks it picks the resistor. No, it picks the capacitor first, 200 microfarad, and then solve for the resistor here. So a problem like this, the key is to have the ripple formula, understand how to calculate the peak voltage across the capacitor, and then come up with reasonable values for the capacitor and the resistor. And that's just a simulation of the circuit. And full wave can appear in two versions. This is a 4-bridge full wave. At the lower part, this is a 2-diode full wave. Usually in the simulation, this transformer is replaced with, and if you're familiar with your homework 1 assignment on those rectifiers, these transformers are replaced with signal generators to generate frequencies. So the key part again is the ripple is the peak times the period over 2 times resistor capacitor. So calculate the peak for the 4-diode bridge. So what is how many diode drops in the 4-diode bridge to calculate the peak?
It's 2.
The 2. And in this version, how many diode drops to calculate the peak?
It's 1.
One. So you have to remember that difference. If the problem is a 4-bridge or 4-wave, the capacitor voltage, there are 2 diode drops across before we get to the capacitor. If it's a 4-wave 2-diode bridge, then there's 1 diode drop before we get to the capacitor. And here's a version of a schematic. This is actually a single tap full-wave rectifier. These 2 function generators are just replacing the transformer, and it gives some specs. You want to approve DC voltage 15 minus 1 diode drop. So this is the 15 volts here. So this voltage here is 15 minus 0.7. And then we want a ripple, it says, of 715 millivolts. And it gives the frequency. So to solve it, basically, there's our ripple formula, and make sure we use the right ripple form, because this one, the full wave, has this 2 in the denominator. We calculate the period, 1 over frequency. Our peak then, and we have the peak voltage here is 15 volts minus 0.7, 14.3. We have the period divided by 2 times the ripple in the formula, and pick the capacitor, 100 microfarad, solve for an arbitrary resistor, 227 ohms. So problems like this, as I said, these are not lengthy problems. It's probably the 6-minute type problem. And most of the time you're just going through your calculator. On the exam, expect that try not to spend more than 12 minutes on a problem. That's when you leave plenty of time for later to kind of go back and revise things. You use blue or black ink in the exam. Avoid pencils, because pencils give the sense that I can mark something out and rewrite it. So blue or black ink on the exam. Zener diodes. This is a diode. It's still a PN diode, and the Zener diode can conduct current in the forward direction and conduct current in the reverse direction. So Zener diode has this small slant on the top of it. In the forward direction, the Zener diode behaves as a practical diode. It turns on at 0.7. And when we reverse bias the Zener diode, at some point it breaks down at a Zener voltage. And that voltage is usually stated as a number. And that's it, because from this point here, what we indicated at the beginning is that we do not expect any questions about a full power supply design with a Zener diode. So there won't be questions such as that. And your
Professor? Dr. Peterson?
so here,
Dr. Peterson? That was a silly question, actually.
what is that?
Is the period T the same for half-wave rectifier and full-wave?
Is the series.
The period T 1 over frequency, is that the same for half-wave rectifier?
Yes.
Okay.
Series is 1 over F.
Okay, thank you.
for voltage.
All right, thank you.
So here's a version of a question with two diodes and based on their, at least the identifying, appears to be two Zener diodes. Is given turn-on voltage of 3.3 volts if they're on in reverse, and they're 0.7 volts if they're on in the forward direction. So, and it just up here at the top, it adds into if the cathode and anode voltage in range 0 to 3.3 volts, the Zener is R. So if any number below 3.3 across the Zener is R, and then if the Zener is in the forward direction open, if the voltage across it is 0 to 0.5 volts, then it's also on. Now that says show that both Zener diodes are on. So this problem is taking the guessing out of the question. It's just saying, assume they're both on, specify what type of on state is for each diode, find the diode current and justify your assumption. Now problem's going to have Zener diodes and regular P and silicon diodes in the same, but just from observing the schematic, two Zener diodes, you have three sections. It's a Kirchhoff's current law, and you notice the R that the draw engineer here. If this circuit is working properly, the current through Zener D2 has to flow in this direction, and D1 is operating as a Zener diode. Current must flow in the reverse direction. You notice all the currents are flowing towards ground here. So now justify that they're both on. So the first starts out if D1 is on as a Zener, a 3.3 volt Zener, then what's the voltage here? If D1 is on at the 3.0 volt Zener, what is the voltage at this point?
6.7.
It's 3.3. That's the largest the voltage can get here, but the Zener will turn on and keep this voltage at exactly pretty close to 3.3. So V1 is equal to V Zener 3.3. For Zener D2 to be on, current must be flowing from the anode to the cathode, which means this is operating as a 0.7 volt diode. And the voltage of V2 will be V sub 1 minus 1 diode watt. Well, 3.3 minus 0.7 will be 2.6 volts. And so far, this voltage is positive, this voltage is positive. So far, there's no contradiction. So now, the question said to find the diode current and the KCL current. So now, at the lower part, the current through resistor R1, that's the main resistor here, is 10 volts minus this volt, the Zener volt, 10 minus 3.3 over 1K, 6.7 milliamp. The current through resistor R2 is the voltage V2 over R2, and up here V2 was solved as 2.6 over 1K, so it's 2.6 milliamp. So the unknown current through V1 is the difference between the current in R1 and the resistor R2 current. So there's the KCL equation to calculate the third current to the Zener. 6.7 minus 2.6 to 4.1 milliamp. This number is positive and is consistent with the initial assumptions that both Zener are on. Spend time with a simple circuit like this. As I indicated, always try the easy guess first. This circuit didn't come up with any contradictions. And just imagine circuits like this that include Zener diodes and regular diodes. And now this circuit here, first observe the circuit. There are no Zener diodes in the circuit. And The diode is short circuited on, so these are ideal diodes, open circuit if on. So it's asking find the three voltages, V1, V2, and V3. And we're basically observing that current, it will flow from the 10 volts towards ground. The current must flow in this direction, and it also can flow in this direction. We have three diodes in series. If any one of the diodes is on, then all three must be on. So D4 is a single diode. So if that, the assumption just says find the three voltages and justify your assumption. So the first easy guess, all diodes are on. Is this statement here true?
Yeah.
Yeah.
V2 to V3 was 0. Because they become wires. Now, the current through resistor R1 is V minus V1 over R1, and V1 is 500 ohms divided by 1K plus 500 ohms. So V1 becomes a voltage divider. The two 1K resistors become in parallel with each other once V2 and V3 become grounded. So the current through R1 is the voltage through at V1 is just a voltage divider, 3.3 volts. The current through resistor R3 is 10 minus 3.3 volts. We get 3.3 milliamps. The current through resistor R2 is V1 V minus 3.3 over 1K, 3.3 milliamp. And then the current from the 10 volt battery basically is just the sum of these two, 3.3 plus 3.3. So it's a problem without a Zener, but I'd say probably on the midterm. Now, if we have a problem, it's going to be, it will have a Zener diode and regular diodes in the circuit. And you just have to decide if the diodes are ideal or are they practical models.
Where did the 500 ohm come from?
Here, because V1 and V2 become ground, and there's a wire across here, and 1K and 1K are in parallel with each other.
Okay.
Okay, so it's a voltage, 1K in series with a 500 ohm resistor, and that's a voltage divider. And another question here, this has it has a Zener and a regular diode in the circuit. And reading the question says, use a practical model for the diode